Hello, this is Dr. Polig, and I'm going to answer questions 1 through 4 on geometric optics, page 421 and page 421. So let's go right into question number 1. So you want to see your entire body in a flat mirror. Do you need the mirror that is tall as you are? Okay, well, let's draw an image of you here, and here's you very briefly, and this is a mirror right here. This is your eye. There's light. This is in a well-lit room, and there's light coming from all parts of your body, but in particular from your eye. The light's coming out from your eye, hits the mirror, and reflects back onto you. Notice light coming from your feet. Light from your feet is scattered in all directions, but in particular there's a point over here in the mirror where the light from your feet comes right to this point. We use the law of reflection that we draw the normal, that the angle of incidence is equal to the angle of reflection. These two angles are equal to each other, and this reflected ray comes right back to your eye. And so notice that this is how you see your feet. The feet are seen from this ray of light that comes from the feet, hits the mirror, bounces off, and comes to your eye. So your height is h, but the length of mirror you need, and you can see from the geometry of the situation and the symmetry that we have here from the angles, the length of mirror that you actually need to see your full length is actually h over 2. Okay. And question number 2. You want a curved mirror that will sharply focus horizontal lights down to a single point. Should you use a parabolic or a spherical mirror? The answer is parabolic. Parabolic mirrors, and this is in your book, parabolic mirrors will focus down to a single point. Spherical mirrors do not. They will focus down to a small region, but it won't be a singular point that you would get from as if it were a parabolic mirror. Okay, question number 3. Explain the difference between a virtual and a real image. Let's go back up here to question 1 and explore more. We know that when you look in a mirror, you're going to see your image. It's a virtual image. It's not a real image. So if this is you over here, you're going to see yourself. Your image is behind the mirror. So this is what you're going to see. The eye, you will see your eye as coming from the eye in the image, and you will see your feet as coming from the feet in the image. Notice that these rays are virtual. These are virtual rays, and if you're standing, let's say, 3 feet in front of the mirror, your image will be as seen as if it were 3 feet behind the mirror. So the light ray coming from your foot, this is a real ray. It reflects and comes to your eye, but your eye perceives it behind the mirror as a virtual ray, as over here. So the image here is a virtual image. Notice that you cannot come and touch the image. If you were to touch the image, you'd have to break through the mirror to get to the image. That's a virtual image. It's a virtual image. A real image, for instance, can be formed with the convex lens, where we form the image on a piece of paper or on a wall. This is an image that can be you can see the image, but it's a real image because you can place it onto a surface. Question number 4, let me scroll a little bit. Question number 4 is, when you look at a pencil in a glass of water, this is water, this is the pencil, you'll perceive it as if it's bent. You see this effect in glasses of water, but also in swimming pools. How do we explain this? I'm going to look I'm going to look as if I'm looking down at this image. And so if I'm looking down at this image, I'm going to redraw it over here. I'm going to draw the cup as a square container. This is a container of water over here, and this is air. Say the pencil is located right here. This is where the real pencil is located, in the tank of water. This is your eye over here, and you're looking at the pencil. Now imagine, however, that there's a ray the ray of laser light coming out from your eye, and it's going to be directed to the pencil. How would that laser light have to travel to go from your eye to the pencil? I'm going to send it in a certain direction, right here. At this is a laser ray. I draw a normal. This is a normal, and it bends toward the normal, and it would hit the pencil right here. So Snell's law explains this bending of the laser light from air, less dense media, into more dense media, where this angle is smaller than this angle. Okay, now in reality, light is scattering from the pencil and coming back. So light from the pencil is coming back this way. So working this backwards, light from the pencil comes through the water, hits this interface, and will bend out toward your eye. Now your eye perceives it as coming back here. So the ray of light from the pencil will be bent out to you in this fashion, but your eye perceives it as coming back here. This is a virtual ray. Notice that if you flip back to this image over here, what we see down here below the water surface is the extension of the pencil bent, because that's explained by these virtual rays over here. What we see above the water is simply the pencil coming, the light from the pencil coming directly at us in the air. These images have to meet at the surface, and if you think about this, this explains why you see this effect, this bending effect right there. Well, I hope that makes sense very briefly, and we'll have more videos that will do more of the questions.